Hi, this is Mr. Manley. In this video, I am going to look at solving word problems that use this growth equation. And this growth equation is often associated with compound interest, but it doesn't have to involve money, doesn't have to involve interest. But we will start off with the first application that does use that. The variables in this equation are A, which is the amount at time t. P is the initial amount at the start of the problem, usually time t equals 0. R is the rate, and this is as a decimal. Remember to convert your percentage, so it's a percent rate that is converted to decimal form. So move the decimal place 2 to the left. N, let's actually do T first. T is time, often in years, but that could vary. And then finally we have N, which is 1 if it's annual, 2 for semi-annual, 4 for quarterly, 12 for monthly, and if we have continuous compounding, that would kind of seem like you'd want it to be infinite, but infinity is not a number that we can plug in for n. And what actually happens here is that if it's continuous, we switch to this equation, A equals P e to the RT. And you should know what E is. You should know that E is approximately 2.718. But there is a calculator key for E for any calculator that you're using. And the PRT of that equation is the same as the PRT of the other compound equation. So take that all in, and then we'll move on and do some problems here. The first problem here is your typical application of the growth equation. It's a compound interest problem with an investment, and we want to know how much money we have after a certain period of time. So in this case, I've got, I'm looking for the A, and it is up here after 9 years. So using some good mathematical notation here, I'm going to write that, which means A of 9 or A after 9 years. And then my P is the initial amount, which here, P stands for principal, by the way. There's P for principal. The principal of $5,000, that's our initial amount. And then 1 plus R, and that's the rate, but we're going to go as a decimal, right? So we move the decimal place 2 to the left. Over N. Where's the compounding? This says compounding annually. And when we compound annually, N equals 1. And then we're going to have annual compounding for this N, and T we said is 9. And that's all there is to it. Now it's a calculator key in, and we'll get the amount of money that we would have after 9 years. And there's the amount. What it said? It said round to the nearest dollar. Do pay attention to that. So I haven't rounded it to the nearest dollar here yet. That's what the calculator gave me. And of course, rounding to the nearest dollar, I would say that it's $6,964. Let's look at another one here. Now here we don't have any money. Still going to use the same equation though. So I'm going to have A, and this says after 13 years. So I'm going to do A of 13. equals, and here my initial amount is a forest, like how much area of land is covered by a forest, and it's 33,700, and that's my principal or my initial amount. And then I have 1 plus, now look at this though, decreases by 6%. So that's going to be a negative. So that's going to be 1 plus a negative. Again, convert the decimal to a decimal, or convert the percent to a decimal form, minus 0.06. This is, now in problems like this, in really any problem except an interest rate or a growth of money problem, the compounding is going to be annually. So we're going to, this is going to be over 1, but really don't need to show that. And then to the t power, which is 13 years in this case. And again, I'm at the point of a calculator key in. You might want to key that in yourself to make sure that you're following along correctly. But yeah, we've got 1 plus a negative 0.06, so that'll be 1 minus 0.06. And let's look at, it says to the nearest kilometer. So taking that key in that I got, I'm going to say 1,655 kilometers squared, right? Squared. And that'll be my solution there. Okay, here is a money problem, but it's money that is we're decreasing in value. Value decreases. This is going to look just like the previous problem. The amount here, it's after 5 years. Have an initial amount. 1 plus, I'm decreasing, so that's negative 0.03 for the, actually, it's not. It's negative 0.3. If I move the decimal place 2 to the left on 30%, I'm going to get to 0.3. And then 5 years. So I'm going to raise that to the 5th power. And I've got another calculator key in. And always be paying attention to the context here. I mean, what's happening is I've got a computer that's worth $1,250 when I buy it, and we're trying to make some calculation about how much it's worth after 5 years, based upon this depreciation, would be the word for it, of 30% per year. And I'm getting 210.09, but it does say round to the nearest dollar. So my answer is $210. And one more. Now this one is there's a little bit hidden in here. Some of it's the same, but definitely some is hidden, and we have to make a little bit of a shift. Like just for one, I've been going A of, and then I'm going to say how many years. Well, there aren't years involved here. There are what are called half-lives. But in this context, the half-life gets treated the same way as the year. So it's going to be A of 6. So instead of after 6 years, I would say after 6 half-lives. And then I'm going to have an initial amount. That's pretty straightforward here. It tells me that my starting amount is 195 grams. All right. And then this is what's kind of buried in here, is that the half-life is the amount of time it takes the isotope to be reduced by half. Well, what's reduced by half? What is that? That's a decrease of 50%, right? So I'm going to go like this. 1 plus negative 0.5. So just like in the previous problem, I was adding a negative percentage as it was decreasing. I'm doing the same thing here. I'm adding negative 50%. And how many times am I doing that? 6 times. And down to the calculator key in. And I get 3.05. Rounding to the nearest gram, that'll be 3 grams. So we see 4 different applications of this growth equation here. And the context change and the units vary, but it all looks the same, right? We have a starting amount, a rate, and a time. Time usually in years, but in the last one there we saw the time was in number of half-lives. Those all look pretty doable, I hope, and you can keep your eye out for other sorts of variations on this, where you have an initial amount, a change in rate, and an amount of time that you are applying that change in rate, perhaps in years, but it could be in other units as well.